Good morning everyone. So, previous class we have learned about what are surface properties and what are the different techniques we can use for characterizing those surface properties. Today we will be learning about the bulk properties. So, what are bulk properties? So, other than the outer surface of a material, all other section is bulk section only. So, for the material to be used for the implant, first that bulk property has to be satisfied. So, that it has to be mimicking the already existing natural material. Then only we can go for surface analysis and those things for making it more biocompatible. So, what are the bulk properties? They are elastic behavior, whether it can be extended based on the application, stress and strain, tension, compression and shear stress, fatigue and creep. Bulk property is totally different from surface, where it will not have any reaction with the system, but it is majorly for the orthopedic implants where there is a load bearing applications and all involved. So, why it is important? Because if you consider the orthopedic implants, once you surgically insert it into the body, it has to be there for lifelong and it has to maintain its function all over that period. To have that capability, we have to characterize that mechanical property of the implants. So, consider the invertebral disc which is inserted into the vertebra of a human. So, for each position the load applied onto that invertebral disc is different. As you can see, in normal supine position which is lying down, it is the load on the disc could be 294 Newton only. But if you are standing and walking and all, it increases gradually due to the force applied on the vertebra, and if you are lifting, that load would be further increased. So, your material has to have that wide range of load bearing capacity, so that it can be in the host system for prolonged period of time, because if there is a failure and if you are inserting an implant at the age of 30, around 50, if it fails, then you have to go for again surgery which has a higher risk and all. So, bulk property thus plays a major role for the longer patency of the implant. And what are the major obstacles in these bulk properties? One is corrosion, and due to the excessive usage of the implant inside the body, the material can break down into smaller pieces, which will causes further complication in the biological system. Okay. So, the fundamental concepts in the mechanical properties are stress. Stress is when an force is applied onto the surface, that is called stress. So, the mathematical term is stress equal to force by area. So, you are applying a force on a specific cross sectional of a material. So, that is the stress. So, based on this stress, the material will go and deformation. So, if there is a dental implant, so while you are eating and also that stress would be applied on the dental implant. So, that has to maintain its integrity. So, that deformation is called strain. So, strain is change in the length by original length, initial length. So, based on these two factors, there is a relation called Hooke's law, which introduces a new parameter called Young's modulus, which is a ratio of stress by strain. So, this is an important and commonly used parameter in all of the biomaterials for while defining a mechanical property of that material. So, other properties related to these tensile strengths are elastic modulus, yield strength, ultimate tensile strength, ductility and toughness. So, these properties I will explain while explaining this stress strain curve. So, you know what is stress and what is strain. So, if you have a relation based on this stress and strain, if there is a increase in stress, there would be an increase in strain. So, the initial proportionate linear increase is called, in that linear increase, the region is called elastic region. So, in that elastic region, what it represents is, if a material, if it is in the elastic region, even if that strain, due to the strain, if it forms if it deforms into a different structure, then it can retain back into its original structure. It's like a rubber band where you extend it. So if you leave it, it can come back into the original shape, original length. So in that region is called elastic region. So there is a particular region where if you extend it furthermore, it will cause breakage of the rubber band. So that region is called plasticity region, where it cannot come back to its original region. So so the initial region is called elastic region. So up to this, the stress and strain would be very linearly proportional. Then after it, the yield point is there. So after this yield point, the material cannot go back to its original state. Okay, so if you are having an implant polymer materials used for vascular grafts, catheters and all. So if that material, if the force applied on the material is going beyond that yield point, its shape can change into a different one. So that will cause problems while introducing into the biological system. So your material has to be below that yield point, whatever the force which is naturally occurring for that material, the application, based on the application, that should be below that yield point. So the ultimate strength is the maximum load that material can withstand. So considering a hip prosthesis, so if you are introducing into the system, the maximum load where that material can withstand, even if it deforms, that is the ultimate strength. So after that, if you continue to give the load, then that material will break. So that is called rupture strength. So this is a typical stress strain curve, but for different types of biomaterials, the stress strain curve varies, because polymers will have a higher elasticity and everything, whereas ceramics has no elasticity at all. So as you can see, the brittle ceramic aluminum oxides, it has a initial Young's modulus, then after that, if you give a load, it will break. There is no point of elongation or anything for the ceramics. Then for brittle metals like cobalt, chromium alloys and titanium, for ductile metals like titanium alloys and all, there would be a little bit elongation, then after which it breaks down. In polymer also, there is a thermosetting polymers such as epoxy polymers, those kind of polymers, it is very brittle in nature. So it cannot have that elastic point. So these epoxy polymers and all used for adhesive surgical glues and adhesive things. So they will immediately seal up the wounds, so that it shouldn't leak anything. So those materials would be very brittle. So those things won't have any elasticity and all. Then ductile polymers or all other low density polymers, polyethylene, then carbohydrate polymers, all those materials will have a higher range of elasticity, such as PVA, chitosan, polyethylene. So normal plastic polyethylene. So if you can extend, it can go for a very longer length and all. So that polymers will have a different Young's modulus and different plasticity region. So based on this, you have to decide, and the application you are going to use, you have to decide the material and characterize whether these materials has the same property as that of naturally occurring material. So like if you are introducing a new vascular grafts and all, that vascular grafts has to has the mechanical property such that it can withstand the force of the bloodstream passing through that graft. And if you are going for a hip prosthesis and all, so you have to look for how the loads and all applying on the region around the hip prosthesis, so that it doesn't break or it doesn't fall above the yield strength. Okay. So how we can find out all these parameters, Young's modulus, ultimate strength and fracture and that rupture point and all. So that can be found using universal testing machine. So in this machine you can do variety of tests, where each of the test will give a different parameters. So this is how the instrument will look like. So instrument, the bottom one is called mounted head. So it is a immovable head. So the bottom, so you can see the two clamps. So in between those two clamps only we will fix the sample. Okay. So the top one is a movable head. So, in that one it will load cell would be there at the top. So, the load cell will apply the force on the sample. So, and it will tension will applied onto the sample. So, that will introduce stress, and then the change in length will be calculated by the sensors. So, which will, from that we can calculate the ultimate strength, yield strength and rupture point and Young's modulus and all. So, for different application different clamps would be available. As you can see, one is for tension. So, tension stress is where you elongate a sample. So, that is the tension stress. And compression is where you compress the sample, so that the material, how much the load it can compress into a smaller on that material surface. Then bending, where the material would be kept and there would be a bending at a different points and all. So, there is based on the application. So, if you are having a screw plates and all in the legs and this prosthesis, so there the bending would be different based on the how many screws and nuts you are introducing into the plates. So, based on that you can go for 3-point bending, 4-point bending to exactly characterize how that will function inside the biological system. Then torsion and all, so there would be a twisting occurs on the sample. So, this kind of testing will be done for the ligaments and all. So, where the ligaments has to be turned so that it does not break or rupture during that torsion stress. Then in plane shear is mainly for the hip prosthesis, where there would be a metal contact. There would be a shear stress applied whenever that ball and cup would be moving over that plane. So, that will be found out using the shear stress in plane testing. So, all this can be done for different size of samples, different sample dimension and all the metals, polymers, ceramics and everything. So, using this instrument you can find out all the mechanical properties and all. And can see in that sample dimension, it looks like a dog bone shape. So, it is an important factor that if you are keeping a single lengthy rectangular sample and all, so the breakage would occur at the where you are clamping the sample. So, that is not the actual tension stress applied onto that sample. So, they make a dog bone shape, so that the sample at the ends would be thicker, so that it would clamp and the breakage would occur at the sample middle only. So, that will give the exact value of how that stress strain observation will be occurring. So, usually we consider, so when a stress is applied, the strain will instantaneously produced. So, that is how our idea was. So, but it does not actually follow that all over the period. So, consider different parameters such as temperature, frequency and time. So, based on these parameters, with the constant stress also it can have a different strain. So, in the stress strain curve, if you can see the applied stress, the strain varied. So, if you increase the stress, strain varied, but if you applied a constant stress also, the strain can vary. So, that is a dynamic mechanical testing and all. So, why this is important? So, temperature, as I said earlier, dental implants and all, where you can have a change in temperature, like while you eating ice cream or a hot soup. So, the temperature changes. So, the implant should maintain its integrity. So, to identify whether that affects that mechanical property, the same normal room temperature, if you are applying a load onto a material, that will have a different effect when the temperature is very cold. So, those things has to be calculated. Then frequency is how much time a material is being used for that specific application. Consider a hip prosthesis where it has to move while walking, how much distance you are walking and all, based on that the frequency varies. Consider the hot valves and all. So, hot valves has to function lot number of times. For a minute it has to beat for around 72 beats. So, consider for a minute it is like that, then for a day how much beats it has to be there, and for a year and for a prolonged period of time, how much time the valves has to open and close. So, over those periods what happens is the material is in contact with the nearby surfaces and all. So, there would be some corrosion, there would be some surface etching and erosion that will reduce the efficiency of that material. So, those factors has to be tested before clinically use that hot valves and these materials and all. So, what are these properties changing based on this frequency and time or. So, time dependent properties are some of the, there are a lot of properties. So, these are the widely used properties, creep or recovery test, relaxation test. So, creep or recovery test is that it is where in creep or recovery test the stress would be maintained constant, whereas the strain would vary. So, if you consider a ligament, so as you can see in the figure, the weight Wt has been load, that is the load has been given. So, when it is given at the time point t, it will not elongate if it is within that linear range of the stress strain curve. After a particular period of time, it tends to elongate. Okay. So, that is that percentage elongation changing, that is what it is changing. So, how much that time can affect that strain on based on a constant stress. So, that is creep or recovery test. Then relaxation test, it is exact opposite of the creep test, where the strain would be kept constant, the elongation would be kept constant, but the load will vary. So, how much load it can vary based to maintain that elongation. So, these things would be very useful when you are designing a new material and all, so that the material should not go to a point where it cannot recover its original state back. Okay. So, for those things these time dependent properties will involve, and to identify that material prolonged usage we will study these time dependent properties. Frequency dependent properties. So, frequency dependent properties, as I have said earlier, the number of frequency your material is being used, like in the hot valves and hip prosthesis. So, wear and tear, it is the major problem in orthopedic implants, where the material would be in contact with the nearby materials and all. So, due to the frequency, high number of frequency we are using that material inside the biological system, the surface will get eroded and that will lose its functionality, lose its efficiency. Fatigue is again the same thing, where you are not in fatigue, you are below the yield point only. The number of the load we are giving is below the yield point only, but due to the over usage of the implants for that application, the material will lose its efficiency, that is called fatigue, it will lose its functionality. So, this usually happens when the material you are designing, it should be almost similar to that natural material, like the metal implants, it should be similar to the bone already present. If it is above also, what happens is that there is a stress shielding effect, it can happen. So, stress shielding effect is an effect where if a material can have a load of around 500 Newton, if we make that material into a 1000 Newton, it can have that much capacity of 1000 Newton material. What happens it can have that all the load by itself, and it will not pass on to the nearby bones and all. So, what happens due to that is the bones surrounding that material will get lose its integrity and it would be weaker compared to the normal bones. So, that is by this material it is shielding the stress of the nearby natural materials and all, thereby reducing its integrity. So, that is one of a major problem in orthopedic implants. So, those things will come when fatigue is also involved. So, it can shield the stress of the load and thereby reducing the integrity of the bone implants. So, those are the basic properties and characterization we can do for the bulk properties of the material. Consider hydrogels and scaffolds. So, those have different properties rather than these polymer films and metal implants and all. So, you might have already studied what are hydrogels and scaffolds. So, hydrogels are gels which can have a water intake, higher amount of water intake, and scaffolds are polymeric scaffolds which can be used for the cell tissue regeneration process and all. So, what are the properties important for these hydrogels and scaffolds? Some basic properties which defines them. So, you can do all the surface characterization and bulk characterization for these hydrogels and scaffolds also. Other than those properties, these properties also involved. Porosity, swelling, degradation, kinetics, and the thermal behavior. So, porosity. So, porosity for a scaffold, porosity is an important factor because porosity will help in cell attachment in depth of that scaffold, and the number of pores will help in transfer of nutrients inside and outside the scaffolds. So, to identify the porosity of the material tissue engineering scaffold, normal techniques like SEM, TEM, mercury porosimeter and gas pycnometry can be used. So, in TEM and SEM you can visually see the porous structure. So, as you can see the SEM image, the porous scaffold is seen, but in SEM image you can see at the surface only. So, you cannot say it confirmed that inside also the porous structure would be there. Maybe the inside it would be a compact bulk structure and the surface would be a porous structure. In TEM, you can actually say that the material is completely porous because due to the transmission electrons, you can see what is inside the material and all. So, if a material is completely porous inside, you can find out using that TEM. Other than these sophisticated techniques, you can use mercury porosimeter and gas pycnometry, which uses Archimedes principle of liquid displacement, where you have how the experiment for this finding the porosity goes is that you will have a liquid. In mercury porosimeter, you will insert the porous structure inside. So, the porous, and you apply a vacuum also. So, the air would be sucked out of the system and all the pores inside will be filled by mercury. So, those by that then you take out the scaffold and weigh the amount of scaffold before keeping into that mercury, and after that, and based on the volume you can actually calculate the porosity. So, mercury porosimeter and gas pycnometry, it involves gas, and commonly used another liquid is that ethanol. So, by ethanol, because it won't involve in swelling of the materials and all. Most of the materials would be hydrophilic, so it can, if you are using water and all, it can absorb water and it can swell and all. It is not actually the porous volume. So, the volume would be based on the polymer scaffold also. So, using ethanol will have a better better than the water experiment. So, porosity formula is that final weight minus initial weight by volume and density of the ethanol used. So, how much of volume and density of the ethanol you are using. So, that will give you the porosity of the scaffold. Okay. So, swelling study is predominantly used for hydrogels because the uptake of water is majorly influences the kinetics of the molecules loading and releasing from the gels. So, a material which can swell faster can mean that the water intake is higher, so that the nutrients or any other drugs or molecules which you are incorporating into the hydrogel can be released faster. So, if swelling is slower, then the release would be slower. So, that defines how the kinetics mostly in drug delivery application and all, how these kinetics would be factored would be affected by this swelling study. So, for swelling analysis, similar to that, what you do is you weigh the samples before keeping it into water, then you keep it in water, then you again weigh the samples. So, that will the difference in that weight by the initial weight, final weight is the percentage degree of swelling. So, usually for hydrogels, for the application wise, you can actually use this degree of swelling to understand that the rate of drug release and all. So, if it is uncross linked polymer hydrogels and all, the swelling would be faster, and if it is a cross linked hydrogel, the swelling would be slower. So, to understand the kinetics of the release profile, you can use this swelling, you can study this swelling. So, degradation. So, degradation is an important parameter for both the hydrogels and scaffolds, because nowadays most of the implants are coming as biodegradable implants, where when it is implanted into the body, instead of having another surgery to remove those implants, these things can degrade by itself, such as the switches, resorbable screws and all, where you implant it for metal plates and sutures for internal sutures and all. So, over the period, initially it should function like a normal suture, where it should have all the mechanical property and all the physical property of the like the normal suture. Then after over the period of time, when the wound heals, that should be degraded by the biological system in the, and it should be washed away from the system. So, this should be tested with the biological fluids and enzymes, so based on the application you are using. So, the biodegradation is calculated by initial weight minus final weight after it is degraded by the final weight will give you the biodegradation. So, this will help you understand how long a material can degrade. So, based on that you can design them. So, if you want your material to be degraded within a week or within a month, then you have to complete degradation should be there within the month. The final value will be around 0 or 2, so that it should be completely replaced by the natural tissue. Okay. So, those are the normal physiochemical properties for the scaffolds and hydrogels. Coming into thermal behavior. So, thermal behaviors, like I said, for implants, for dental implants and for normal polymeric materials also, you have to understand the effect of temperature on the material. So, that can be found out using DSE and TGA. So, this is a commonly used, these two are commonly used techniques. Other than this, there are other thermal characterization techniques also. So, DSE, it involves what it actually finds out is that the material melting point, crystallization point, then the glass transition temperature, then the phase change of the polymers. So, those things can be found out using differential scanning calorimeter. So, the instrumentation involves as you can see in the picture, there are two, one is a reference and another is a sample. In the sample pan we will keep our material, and in the reference pan it would be a empty pan, or you can have a reference comparable materials and all. So, what happens is you will apply a constant temperature onto the both the sample and reference at the same time at the same temperature. So, what happens is that if your material exert heats, like releases heat by exothermic reaction or endothermic reaction, it absorbs heat, there would be a change in the heat flow. So, that would be detected. So, based on that you can actually plot this DSE thermogram, where you can find out the melting point, crystallization point and degradation point of the materials. So, as you can see, the first when it polymeric materials, if it is amorphous polymers, it will go a glass transition change. So, it can go from brittle nature into a rubbery nature. So, above glass transition temperature, the molecule will be arranged randomly. So, that will have a rubbery nature, that is the temperature called glass transition temperature. So, glass transition temperature, after that it will molecules will arrange orderly fashion, where it is you can find out the crystallization temperature. So, after that molecule tends to melt. So, that is the melting temperature. Then if there is a chemical reaction due to the temperature, so that is the exothermic behavior you are seeing. Then finally, the degradation occurs, where the material is completely degraded due to the temperature. So, these temperatures and all these temperatures are very essential when you are using a thermoresponsive gels and other temperature involving implants and devices. For it can also be used for characterizing new biomaterial, where you are having a cross linked or a mixture of two materials and all. There would be a difference in or shifting in the temperature in the glass transition temperature, and change in melting temperature and all, it will occur, because higher the cross linking, the melting temperature will vary. So, based on that you can identify that your cross link has occurred, or your material properties has changed due to the incorporation of a new molecule into your samples and all. So, that can be found out using this differential scanning colorimeter. Thermogravity analysis is similar to DSE only, the mechanism is similar to DSE only, but here it involves as the name suggests the gravimetry, which is weighing of the material. So, the instrumentation is almost similar. Nowadays the advanced instruments has both DSE and TGA is available. So, where in the DSE, where you can observe the change in temperature due to the material when the heat is supplied. Here, due to the heat is supplied, you can actually measure the minute change in the weight. So, you will use a sample of around 20 mg or 5 mg only for each of them. So, that can be, that minute change in temperature can be observed using this thermogravimetric analysis. So, this mainly helps us to identify how the degradation occurs for the material and all. So, typical thermogram will looks like that right corner, you can see that. So, around 100 degrees Celsius due to the increase in, so in DSE and TGA there would be a constant increase in temperature we will be supplying. So, initial increase in temperature, there would be a volatile compounds like moisture, water adsorbed, or any solvents present, it would get evaporated from the system. So, that would be a, you can see there is a decrease in the weight percentage, that is the initial stage. Then the second stage would be the decrease in the polymer, decrease in the weight due to the polymer degradation. So, that is in the second stage. Then the final stage, where it is completely turned out into an ash, which is degraded polymers, everything has been completely turned into carbon. Okay. So, the interpretation for this TGA analysis, it if it is there is your material is not affected by any temperature and all, the line would be a very straight line. Then in the curve 2, you can see there is a decreasing, sudden decrease, and it became stabilized. That usually denotes that your material some moisture or some solvents are there, so which is getting evaporated, not a degradation of a compound or molecule present on the scaffolds. That is the curve 2. Then in curve 3, it is a single stage decomposition. So, if your material is made up of a single polymer or single material metals or something, ceramics and all. So, there would be a single degradation of that particular molecule only. So, that can be observed due to the single loss of the weight. If your material is having a multiple polymers, like interpenetrating networks, where you have a couple of polymers, or alloys where you use silver, titanium alloys and all. So, those will have each material will have a different degradation temperature. So, the lower degradation temperature, first step would be those materials will get degraded, then simultaneously based on the degradation temperature it varies. In step 5, if it is not a stepwise, if it is just gradually decreasing, it means that you are actually heating it very fast, so that your instrument cannot measure the exact weight of that material or scaffolds present. There can be some increase in weight also. That happens when your material is reactive to the atmosphere present inside the system. So, usually it would be an inert atmosphere such as we can use such as nitrogen or argon and all. But if you are using a normal atmospheric condition, there would be oxidation occurs, which can lead to the increase in the weight of the material. So, the final one is again after decomposition, it can, those decomposition products can interact with the atmospheric compounds and reactive species, so that it can lead to an increase in that weight. So, this can also happen in magnetic samples also, there would be an increase in weight also. So, by characterizing these thermal properties, you will know that your material is pure, or if you are, whatever you are incorporating into your material can have any thermal effect onto the final material. So, those things can be analyzed using these techniques and all. So, understanding these both the bulk properties and the surface properties will have a clear idea of how exactly you want to use that material for your applications and all. So, after finishing these two characterization, you have to go for your biological characterization, where you can check for the protein adsorption, cell attachment, and if you are working on antibacterial adhesion or biofilm formation to avoid biofilm formation. So, those things and all come under the biological characterization, how effectively it can improve or decrease the attachment of the biological system. So, before going that, you have to understand these parameters, and these characterization techniques has to be done for all the materials you are trying to do.